Hello everyone. In our previous lecture, we considered this spring mass balance system and we realized that if we know the eigenvalues for this particular problem, then we can identify the frequency with which our system is oscillating. Now we will study how to find eigenvalues numerically. In this lecture, first we will explore the polynomial method, and in the upcoming lecture we will discuss power method. Now in order to understand the polynomial method, we will consider a problem of slender beam which is subjected to some compressive load P. So once this load P exceeds some critical value, the beam will take this kind of shape, and this phenomena is called buckling of beam. Now the equation which governs this phenomena is written here, where on the left hand side we have d square y by dx square, which specifies curvature of the beam. Here E is modulus of elasticity, I is moment of inertia of the cross section about its neutral axis, and m is the bending moment. Now if you see this particular figure, then in the transverse direction we have y, and in the lengthwise direction we have x coordinate. So at any particular x, the bending moment m is written as compressive load P into this transverse distance y. That's why bending moment m is written as P into y. If you carefully observe its direction, then it is in the anti-clockwise direction, so we can put minus sign here. So that's why our bending moment m is equal to minus p into y. Now we will substitute this bending moment m is equal to minus p into y in our main equation. So this is our resultant equation. Now we will assume that p over ei is equal to small p square. So after putting this value, we will get d square y by dx square is equal to minus p square into y. Now we will take this particular term to the left hand side, so we'll have d square y by dx square plus p square y is equal to 0. Now let's talk about the boundary conditions. So this is our main problem, and this is the end at x equal to 0, and this is the end at x equal to L. So if you carefully look at this deflection of this beam, then the deflection of beam for x equal to 0 is also 0, and the deflection of beam at x equal to L is also equal to 0. So our boundary condition is y at x equal to 0 is 0, and y at x equal to L is equal to 0. Now the general solution of our equation, that is d square y by dx square plus p square y equal to 0, is given by y equal to a sin px plus b cos px, where a and b are coefficient which are evaluated using our boundary conditions. So let's first apply first boundary condition, that is at x equal to 0, y is equal to 0. So we'll put here x equal to 0, so you will get sin 0, and here we will get b cos 0, and obviously on the left hand side we will have 0. So using first boundary condition, we will get 0 equal to a sin 0 plus b cos 0. Now sin 0 is 0 and b cos 0, here cos 0 is equal to 1, so you will left with b is equal to 0. So now onwards we will not use this b term because b is already 0. So while applying second boundary condition, we will consider only the first term, right? So now let's apply the second boundary condition, that is at x equal to L, y is equal to 0. So after putting this value, here we will have 0, and here we will have L, and we are not going to consider this term because b is 0. So using second boundary condition, we will get 0 equal to a sin pl. Now a cannot be 0 because b is already 0, and if you put a equal to 0, then it becomes trivial solution. So we'll put sin pl is equal to 0. Now when pl is equal to n pi, where n is equal to 1, 2, 3, 4 and so on, this condition will satisfy our equation, right? So if you take this L terms on the right hand side, we'll get p is equal to n pi over L, where n is equal to 1, 2, 3 and so on. So these p values are nothing but our eigenvalues for this column. Now for different values of n, we will get different eigenvalues. Now what is the physical significance of eigenvalues in our column problem? So each eigenvalues corresponds to a way in which the column buckles. So this is the equation of our eigenvalues. When we put n equal to 1, we will have p is equal to pi over L. For this eigenvalues, our column takes this shape. When we put n equal to 2, we will have this kind of shape. For n equal to 3 and n equal to 4, we will get this kind of shape. Now if you recall our previous slide, then we approximated p over ei is equal to p square. Now here we will substitute n pi over L, so we will get n square pi square over L square is equal to P over EI. Now what is the usage of this equation? So this equation will be used to calculate compressive load P acting on this column. So P is written as n square P square EI over L square. Now this equation will be used to calculate critical load for this column. Now what is critical load? So critical load is the load at which this first band is observed, right? And this first band is corresponds to n equal to 1. So when we put n equal to 1, we will get our critical load, that is P critical is equal to pi square EI over L square. So our compressive load P should be less than the P critical for our safer limit. Now let length of this column is 3 meter, then by substituting L equal to 3 here and by varying n is equal to 1, 2, 3, 4, we will get 4 different eigenvalues. So this is the 4 different eigenvalues corresponding to these 4 different shapes. Right, so this is our analytical values of eigenvalues. What is the usage of these analytical results? So this value will be used to evaluate our numerical prediction of eigenvalues, which we will discuss in our upcoming slides. So in this course we will learn two numerical methods to calculate eigenvalues of our problem. The first one is polynomial method, which we will cover in this class, and the second one is the power method, which we will cover in our next class. So let's start our polynomial method. So this is the equation which needs to be solved. So if you carefully observe this particular term, then this is the expression of f double prime x. So if you recall our first class of finite difference method, then we derived central difference approximation for f double prime x. So we will use that particular approximation to replace this d square y by dx square term. So by using our FDM knowledge, we will use yi plus 1 minus 2 of yi plus y of I minus 1 divided by h square plus p square yi is equal to 0, where h is the distance between two nodes. Now we will multiply h square with this equation, so we will get y of I plus 1 minus 2 of yi plus y of I minus 1 plus p square h square yi is equal to 0. Now we will try to club this yi and yi together, so we will get yi minus 1, which is this term, minus 2 minus p square h square yi, which are this term and this term, plus y of I plus 1 is equal to 0. Now let's divide our column into two different segments. So this is the segment number 1 and this is segment number 2, and length of this column is 3, so h is equal to 3 by 2, which is equal to 1.5. Now we know that this equation is only applicable to intermediate node. So node number 0 and node number 2 are boundary nodes, whereas node number 1 is intermediate nodes. So now let's apply this equation to intermediate node 1. So by putting I equal to 1, we will get y of 0 minus 2 minus p square h square into y1 plus y2 is equal to 0. Now when we apply the boundary condition, then we will realize that the deflection of this node 0 is 0. Likewise, deflection of this node 2 is also 0. Here also we will substitute h is equal to 1.5, so we will get minus 2 minus 2.25 p square into y1 is equal to 0. Now y1 cannot be 0 because this node is anyway going to deform, so we are left with 2 minus 2.25 p square is equal to 0. Now when we solve this equation, we will get p is equal to plus or minus 0.9428. So this is our numerical eigenvalues for the first point. Now if you recall our analytical results which we tabulated in our previous slide, then the actual value for the first eigenvalue was pi by L, which is equal to 1.0472. So our numerical value, that is 0.9428, is having 10% of error. Now let's divide our domain into three segments. So this is segment number 1, segment number 2 and segment number 3. So for this particular case, we will have h is equal to 3 by 3, which is equal to 1, and this is the generalized equation which is applicable to intermediate nodes 1 and 2. So let's apply this equation to node number 1. By substituting I equal to 1, we will get y of 0 minus 2 minus p square h square into y1 plus y2 is equal to 0. Now when we apply boundary condition, we will realize that the deflection of this node is 0, so we'll put y0 is equal to 0, and here we will substitute h is equal to 1, so we will get minus 2 minus p square into y1 plus y2 is equal to 0, and this equation can be written as 2 minus p square into y1 minus y2 is equal to 0. So this is the equation for node number 1. Similarly, let's apply this equation to node number 2. So by putting I equal to 2, we will get y1 minus 2 minus p square h square y2 plus y3 is equal to 0. So here also we will apply boundary condition, that is the deflection of this node y3 is 0 and h is equal to 1. So we will get y1 minus 2 minus p square into y2 is equal to 0, which can be written as y minus y1 plus 2 minus p square into y2 is equal to 0. So let's rewrite these two equations. So this is the equation for node number 1 and this is the equation for node number 2. So these two equations can be written in compact form using matrix. So this is the matrix representation. So if you open this equation, you will get 2 minus p square into y1 minus y2 is equal to 0, which is equation number 1, and minus y1 plus 2 minus p square into y2 is equal to 0, which is equal to equation number 2. So by setting determinant equal to 0, we will get 2 minus p square whole square minus 1 is equal to 0, which can be written as 2 minus p square whole square is equal to 1. So if you solve this equation, you will get p is equal to plus or minus 1 and p is equal to plus or minus 1.7320. So these are two numerical eigenvalues which we solved using polynomial method. Now if you compare these values with our analytical results, then we had for first eigenvalue we had 1.0472 and the second eigenvalue was 2.0944. So our numerical prediction has a error of 4.5% for the first eigenvalue and 17% for the second eigenvalue. Now we will divide our domain into 4 segments. So this is segment number 1, 2, 3 and 4. So h is equal to 3 by 4, that is equal to 0.75. So this is our generalized equation which is applicable to intermediate nodes. So this is intermediate node 1, 2 and 3. So we will apply this equation to node number 1. So by putting I equal to 1, we will get y of 0 minus 2 minus p square h square into y1 plus y2 is equal to 0. Now here we will apply boundary condition, that is the deflection of this boundary node 0 is 0. So here we will have 0 and instead of h we will put 0.75. So by putting this value we will get minus 2 minus 0.5625 p square into y1 plus y2 is equal to 0, which can be written as 2 minus 0.5625 p square into y1 minus y2 is equal to 0. So this is the equation for node number 1. Similarly for node number 2, we will put I equal to 2 in this equation. So we will get y1 minus 2 minus p square h square into y2 plus y3 is equal to 0. Now here we will put h is equal to 0.75. So we will get y1 minus 2 minus 0.5625 p square into y2 plus y3 is equal to 0, which can be written as minus y1 plus 2 minus 0.5625 p square into y2 minus y3 is equal to 0. So this is the equation for node number 2. Similarly for node number 3, we will put I equal to 3. So here we will have y2 minus 2 minus p square h square into y3 plus y4 is equal to 0. So here we will put h is equal to 0.75. So we will get y2 minus 2 minus 0.5625 p square into y3 plus y4 is equal to 0. But we know that the deflection of this node, that is y4, is 0. So we will also remove this term. So we will get minus y2 plus 2 minus 0.5625 p square into y3 is equal to 0. So these three equations can be represented in a compact form using matrix. So in matrix form, this equation is written as follows, and by setting determinant equal to 0, we will get 2 minus 0.5625 p square whole cube minus 2 times 2 minus 0.5625 p square is equal to 0. So by solving this equation, we will get 3 eigenvalues, that is the first eigenvalue is p is equal to plus or minus 1.0205. The second eigenvalue is plus or minus 1.8856 and the third eigenvalue is plus or minus 2.4637. So these three are numerical prediction of our eigenvalues using polynomial method, and these three eigenvalues are our analytical results. Now when we divide our column into 5 equal segments, then we will have h is equal to 3 by 5, that is equal to 0.6, and the resultant equations are represented in a compact form using matrix, and by solving this equation we will get 4 eigenvalues, that is p is equal to plus or minus 1.0301. Then the second eigenvalue is p is equal to plus or minus 1.9593. Then third eigenvalue is p is equal to plus or minus 2.6967, and fourth eigenvalue is plus or minus 3.1702. So these four are numerical prediction, and these four eigenvalues are our analytical results. So this is all about polynomial method, and in the upcoming lecture we will study another method, that is called power method.